I'm very happy to come back to Korea and visit with teacher again and attending this wonderful workshop. I'm also very happy to see two of my previous papers mentioned in the previous talks. Like yesterday, this morning, I heard something about like a Tokachenko mode in a vortex lattice in a first talk. And yesterday, like Professor Han mentioned my toric code work. So what I'm going to discuss today is kind of a combination of here maybe. It's okay. Oh yeah. Some weird line here. Oh. Yeah, maybe try that one. Yeah. This should work. Should be fine. All right. Maybe fine. All right. So what I'm going to discuss today is a combination of spontaneous symmetry breaking and frustration-free Hamiltonian. And for this audience, I don't think I need to have like a introduction for spontaneous symmetry breaking. So let me start from explaining what is frustration-free. So this is like a frustration in quantum many-body systems. So as an example, like here I want to talk about 3 spins, 1, 2, 3. And I want to assume anti-ferromagnetic interaction among 3 spins. Okay, so every spin want to align in an opposite direction. And if I consider this spin configuration, I find this anti-ferromagnetic interaction between spin 1 and 2 are happy, 2 and 3 are happy, but 1 and 3 are not happy, right? So this situation, like no way of making all interactions simultaneously minimized, is called frustration. And the Japanese word for this situation is called tankaku-kankei. And yesterday I learned that the Hangul, Korean word for this word is almost pronounced almost the same way. I don't know how to pronounce it, but yeah, tankaku-kankei, right? Like the same pronunciation. All right. And okay, so this is just like a triangle, like 3 spins. But more generally, Hamiltonian is called frustration-free if it satisfies following properties. So there's a decomposition of Hamiltonian into a local terms, and this decomposition into many terms, so that like each local Hamiltonian are finite ranged. Okay, and the ground state of this Hamiltonian have to minimize all local Hamiltonians simultaneously. Namely, like a local Hamiltonian applies to ground state, gives you the ground state energy of each local Hamiltonian. Okay, and I will set this ground state energy of local Hamiltonian to be 0 by shifting the ground energy origin. Okay, but note that local Hamiltonians do not have to commute with each other. Okay, so this is a definition of frustration freeness in quantum many-body systems. Any questions now? Is this definition clear? Good. So let me give you an example. Maybe you may think this is a very special case, but actually there are many examples. Like for example, this simplest example, like paramagnetic Hamiltonian is of course frustration free, but there are many other examples like Masaoka Hamiltonian, which includes anti-ferromagnetic interaction not only between the nearest neighbor spins, but also like next nearest neighbor spins is also frustration free. The famous example, like AKLT Hamiltonian, includes the square of anti-ferromagnetic interaction for spin 1 system. It's also frustration free. And a toric code model, which is like a 2D model of topological order, is also frustration free. And why are they useful? Because actually, like they can be understood as a representative, like a simplest model of many different phases of condensed matter systems. For example, like this paramagnetic Hamiltonian give you a trivial phase, and Masaoka model actually in the ground state you have spontaneous symmetry breaking of translation symmetry. AKLT Hamiltonian is like a representative Hamiltonian for symmetry protected topological phases. And toric code, of course, gives you a topological order. And we just had like a CPZ model in the previous talk, which gives you a very non-trivial phenomena. That's also, as far as I understand, that's also like a frustration free, right? So because of this richness of the phases represented by frustration free Hamiltonian, I believe it's still worth studying the general property of this this class of Hamiltonians.
I have a question.
Yeah.
So in this case, you only require that the ground state is frustrated free. But is this some more interesting physics if we consider a low energy manifold is frustrated free?
So yeah, but okay, I don't know how to extend this definition to include like a low energy manifold, but I think like for this talk, I want to restrict myself to this precise definition among ground state. Yeah, maybe we can discuss later.
Thank you.
Thank you. So like I also wanted to mention this the ZN extension of toric code, because this model was kind of mentioned yesterday. So what I did is the following. So so this is a toric code model. So I have n level spins on each edges, and I have bracket term and vertex term. And the bracket term is a product of these spins for each bracket, and vertex term is product of x operation for every vertex. And this is frustration free because they commute, and there is no global constraint of writing the ground state that minimizes all terms simultaneously. What we did is to introduce an integer parameter a and modify the operator in this way. So this is like a 4 spins I use to write down this bracket term for this modified Hamiltonian. What I found is that if we do this modification, the ground state degeneracy is modified to this formula. It looks complicated, but what is most important here is that this quantity can be 1, despite the fact that this phase still is a topological ordered phase. For example, like when n is 11, so this like the number of levels of this spin is 11, and this parameter a is 2. In this case, I found that ground state is unique unless both L1 and L2, like system size, both of them are simultaneously an integer multiple of 10, which I think is kind of difficult, right? Like if I give you this model, and if you do numerical simulation, exact diagonalization, you will most likely see a unique ground state, although this phase belongs to a topological order phase. So like I found this model is kind of interesting in that sense, because people believe that topological order phase must have topological degeneracy, right? But this is kind of counterexample unless you are lucky to hit both L1 and L2 being integer multiple of 10.
So in this case, you have the degeneracy on torus, but what happens if you do like different Riemann manifold?
Other manifold. Okay. Actually, I didn't study that part. This result is just for torus, as you say. Yeah. Yeah. Maybe like we can figure out in the coffee break. Yeah. Thanks for the question. Yeah, but what I wanted to say here is that even this non-trivial model belongs to frustration-free class. So the goal of one of the goal of today's talk is to understand general properties and limitations of this class of Hamiltonian, frustration-free Hamiltonians.
Excuse me.
And yes,
can you say so for n greater than 2?
Yeah. So this
it's
is
no longer commuting, right?
Yeah. I still have this property, like
That's still true.
That's still true for this model. Yes.
I see. Okay. Yeah. Mm-hmm.
Yeah, like one form symmetry get modified. Like this is really like a modulated symmetry story. Professor Han talked yesterday. Yeah.
But can you explain what I'm trying to understand, like qualitatively, what new features introduced when you go from two versions of frustration free in one where the HIs don't commute and where they do commute? Is there some new? Is there anything new arises from non-commuting? Or is it should I think of it as
so for example, like this AKLT Hamiltonian or Masaoka Hamiltonian, each term that do not have to commute. So this is not commuting project Hamiltonian. while this is commuting projector. This is also commuting projector. I don't know the general difference between these two classes. I'm just saying, like this frustration-free is a weaker condition than commuting projector. So
Right.
it may represent a wider class of phases, but I don't know, like
if there's some finer distinction.
right.
Okay.
Yeah, that's a really good question, actually.
Thank you.
Thank you so much. All right, any other questions? If not, I'll move on to the real content of this talk. So like my goal is really like to understand the limitation of the frustration-free Hamiltonians. As I told you, like sometimes each phases can be represented by nicely by a frustration-free limit. So is it possible that some phases do not have frustration-free limit? That kind of things I want to understand. So this is outline of my talk. So to set up stage, I will start from my very old work, like more than 10 years ago, about Gaussian bosons in non-relativistic systems. And then I will move on to a newer result about spontaneous symmetry breaking of U1 symmetry in 1+1 dimension. By studying this particular model, I realized the importance of frustration-free nature in this model. And that's the third topic of today's talk. And finally, I will talk about some application of these results towards like a Markov chain Monte Carlo simulation. Okay. So let me start by reviewing the number Gaussian bosons in non-relativistic systems. Okay. Okay. Actually, relativistic systems. So suppose your original Hamiltonian have symmetry group G, which is spontaneously broken down to H. Then this coset space G over H gives you the space of degenerate ground states. Like for this, wine bottle example, degenerate ground states is really like the U1, like a ring, which is the location of this ball, right? Then the number Gaussian bosons are low energy fluctuations within the coset space, and the number of broken generators is given by the number of the dimension of this coset space, which is the difference between the generator of G and H. And number of Gaussian bosons is N energy B. It's always given by the number of broken generators, and that can be explained by writing down effective Lagrangian that is consistent with Lorentz symmetry and internal symmetry. And by expanding this effective Lagrangian to the quadratic power in fluctuation pi, then like I get this number of linear dispersive Gaussian bosons. This is the standard story. And when I modify this story to non-relativistic systems, like our condensed matter world does not necessarily have Lorentz symmetry because of the experimental frame, right? Then this part is unchanged, but the number of number Gaussian bosons is sometimes reduced by this number. And there are many examples like anti-ferromagnet is a standard case, but ferromagnet has one less Gaussian bosons than the number of broken generators, and there are many other examples. So we wanted to have systematic understanding. Then that can be achieved by writing down effective Lagrangian. Again, for Lorentz invariant cases, yes. I don't have to require Gaussian symmetry. I'm just saying, like, I don't assume Lorentz symmetry. That's my definition of Lorentz non-relativistic. Yeah. Thanks for the clarification. Yeah, right. So like now I am allowed to add more terms because I don't assume symmetry that relate time and space direction. But I'm still requiring spatial rotation symmetry for simplicity because that's usually the emergent low energy symmetry. Then I found in addition to this standard two time derivative terms, I have a single time derivative term which can be expanded around pi equals 0 in this way, so that to the quadratic order in field, this is the effective theory I have. Then this rho AB is a skew matrix that is related to the broken generator commutation relation, like this. Okay, so this is a definition of rho AB. And so like a skew matrix in general can be diagonalized this way, block diagonalized this way. And here I have M blocks, and this M is related to the rank of this matrix. And I call this part is type B. This 0 part is type A. And this 0 is a standard case, like I don't have single time derivative term. While type B case, this effective Lagrangian is dominated by a single time derivative term, and I can forget about this quadratic 2-time derivative term. So the counting formula was modified this way. For type A Gaussian bosons, I have 2-time derivatives and 2 special derivatives. They have to match. So they independently produces linearly dispersive number Gaussian bosons, and their counting is given by by this formula. While for type B Gaussian bosons, because of this single time derivative, 2 fields form a canonically conjugate pair. So 2 fields represent only one fluctuation, like this, fluctuation in x direction and y direction merged into a single precession mode. So that's what happened in ferromagnetic example. And by counting the number of type B Gaussian bosons, I find it is precisely given by the half of the rank of the matrix rho. And the dispersion is quadratic in general in this case. So by combining these results, we obtained this counting formula, which this is actually like almost the first PhD project I did during my stay in Berkeley with Thomas, who is the organizer of this workshop, and with Hitoshi. Also, like Hidaka-san sitting in the audience did independent work deriving the same formula. And I think like this kind of situation is nicely written in the book, a recent book by Thomas. All right. So I said, we wanted to have systematic understanding, and I think it is now achieved. And by using this formula, I can correctly predict the number of Gaussian bosons. So this was nice, but the question is this the end of the story? Of course not. Like, and then I want to talk about my recent topic finding. So this is about Mermin-Wagner theorem. So let me start from reviewing the most basic version of the theorem. So this Hohenberg-Mermin-Wagner theorem states that continuous symmetries cannot be broken at finite temperature in dimension equal to or smaller than 2. And by writing D, I mean it is like only special dimension, okay? Like I'm now a condensed matter theorist, so I don't include temporal direction in the counting of D, okay? And so this theorem is actually related to the number Gaussian theorem I just discussed. It says spontaneous symmetry breaking of continuous symmetry implies the presence of gapless excitations. And the proof goes like this. It's like a proof by contradiction. Like suppose a continuous symmetry is indeed broken, then the Gaussian theorem implies the presence of gapless excitations. But in low dimension, this infrared divergence originating from the Gaussian bosons destroys the order by fluctuation. So that's the kind of standard scenario. And this finite temperature version can be extended to 0 temperature version. And counting rule like the statement is modified like this. Continuous symmetries cannot be broken at 0 temperature in dimension equal to or smaller than 1. And this theorem is also known as Coleman theorem because he gave a field theoretic proof assuming Lorentz symmetry. Okay? And the proof is almost the same, except the statement is just modified by 1. But we are going to discuss counterexamples to this T equals 0 version within the internal symmetries. So I found the previous speaker have a very nice work about multiple symmetry breaking, which is spatial symmetry. Today my example is internal symmetry, which is a kind of different scenario. Yes.
Yeah, just want to make a comment. So maybe in the Coleman's case where you have Lorentz invariance, you can make this very general statement that Lorentz invariance unitary and various other assumptions that Coleman makes, then you could then say it very generally. But like for Hohenberg-Mermin-Wagner, I think it's a colloquial interpretation or extension of what is actually proved in those theorems. And I think it's too strong of a statement. There are systems in which, ordered phase is controlled by a non-trivial, non-Gaussian fixed point. And then, this naive interpretation of Hohenberg or extension of Hohenberg-Mermin-Wagner does not apply. It's
maybe
just,
like that is precisely what's next examples we all.
Okay.
Yeah.
So
so let me know like if you're.
I mean, we tend to say this a lot. But
Right.
I remember doing my thesis defense, and Bert Halpern corrected me in where I was making a comment about breakdown of Hohenberg-Mermin-Wagner theorem.
Right. So you're right. Like this is not really a mathematically formulated theorem. So that's why like I put it in quote unquote, right? And so it's no surprise that this theorem has exceptions, but hopefully my new example is a little bit more interesting than the previously known examples. Okay. Any other questions, comments? Yes. I don't hear you actually. Like maybe you need a microphone. Yeah, that's the next slide actually. Like ferromagnetic state, right? Yeah. Okay. But before, like I need to kind of give you a definition, more precise definition of spontaneous symmetry breaking. So like let's resist ourselves to spin models defined by lattice, and I want to write down Hamiltonian as a sum of local interactions, and it has an internal symmetry generated by this generator Q, which is again sum of local charge density, and Hamiltonian and charge operator Q commutes. Then, like I introduce an order parameter O that is given as a commutator of this generator Q and the auxiliary field X. Okay, this is a kind of standard setting, right? Then I apply a symmetry breaking field H by replacing Hamiltonian this way, and I compute the order parameter as a function of H using the ground state of this, Hamiltonian under external field. And I say the symmetry is broken if this expectation value does not vanish when I take H goes to 0 limit after taking thermodynamic limit. Okay, so that's the definition of spontaneous symmetry breaking. And as you asked, the famous, very well-known counterexample to this T equals 0 version of the Mermin-Wagner theorem is this, like a Heisenberg model. And this model have a SU2 symmetry, but here I'm focusing on spin rotation about z-axis generated by z component of spin. And as the order parameter, I'm using x component of spin that is given by the choosing y component of spin as an auxiliary field. Then I do that exercise computing, order parameter, and I find some non-zero value. So I may say, symmetry is broken. In this case, people say, okay, this is fine, trivial, because Hamiltonian and the order parameter commute with each other. So there's no fluctuation to destroy the order, right? Because I can label my ground state as an eigenstate of this, z component of spin. X component of spin. So there is no fluctuation that can destroy the order. In this case, my coset space is a sphere, and the Goldstone boson have spin fluctuation in this model is known to have a quadratic dispersion, which is the representative example of type B Goldstone bosons. Okay? So my new example looks like this. So it is still similar to the Heisenberg model, but now it is modified to XXZ type interaction. So delta is a parameter which can be shifted from 1. Delta equal 1 case is Heisenberg ferromagnet. Now, this is like a XXZ interaction, but I have Hall-spin interaction which looks like this. And this model still have spin rotation symmetry about z-axis. And as an order parameter, I still choose x component of spin. Okay, and see what happens. So this is what I find. I still find a non-zero value of this, order parameter. So I say this U1 symmetry is spontaneously broken. What is surprising for this model is that order parameter and Hamiltonian doesn't commute. But so I said, this, coset space is S1 because, the symmetry to start with was only SO2, not SO3. Okay. And the dispersion for number Gaussian boson is turned out to be still quadratic, and which couldn't be explained by the previous, counting formula I just explained to you. And this will be explained by a frustration-free nature of this model later in this talk. Okay. Any question about this model? Good. Yep.
The reason you're evading the theorem is just that the goldstone is softer. And so, of course, you don't have infrared divergences, and so there's no obstruction.
You're right. Okay, yeah. Right, exactly, yeah. So, exactly. So that's what I'm going to discuss now. Okay. Yes.
It's softer.
Yeah. So. Right. So that's the kind of. Right, but you will see actually like you will see like softer dispersion actually helps. So let me do this.
I'm just saying naive interpretation.
Right.
If it's softer, it should
be a lot more safe, but that's not.
So like to clarify that point, I want to review the proof of Mermin-Wagner theorem given in this paper. Okay. So it is based on the inequality called Bogoliubov inequality. So to use that inequality, it looks like this. It looks complicated, but it's really simple. So I need to perform a Fourier transformation of charge density operator and auxiliary field X. Okay, and Bogoliubov inequality looks like this. It looks complicated, but what is important is that the left-hand side is just order 1 quantity, while in the numerator of the right-hand side, I have order parameter m. Okay, so I want to discuss whether this m is non-zero or not. That's the important point. In the denominator, I have this computation relation of Hamiltonian and charge density operator. And we know that in the limit k goes to 0, this is 0 because we assume symmetry, right? And I approximate this summation by integral. I get this. So order 1 and m squared in the numerator and k squared in the denominator. And unless this integral converges, this is contradiction. So like m must vanish. That's the standard discussion of Mermin-Wagner theorem. Now, if I modify this to t equals 0 version, then I need to replace this to t actually by excitation energy. And actually, like this soft dispersion helps to cancel some part of this k squared part, like in the denominator. So the expectation, like a softer dispersion unfavors order comes from this part, Like say like if you have dipole symmetry, then like this part will not be like a k squared. It can be k quartic or something, so this is unfavored part. But if there's some other mechanism to make this softer, then actually it helps. So there's a kind of two effects like that favors unfavors. So if I have some mechanism to make these Goldstone bosons softer without making this denominator higher order, then actually that helps. Okay. So thank you so much for the question. And in my example, n equal 2, and this denominator is still k squared, so symmetry breaking was allowed in any special dimension. All right. Then the question is, why do we get this quadratic dispersion in this model, or in more general in frustration-free model? All right. So how many minutes do I still have? Okay, good. So now I will make I'm trying to explain what I've been working on in general for frustration-free systems. Again, so this is a recap of the definition. What is important is that like in the frustration-free systems, the ground state of Hamiltonian minimizes all terms of the Hamiltonian simultaneously. And I set ground state energy to be 0. And okay, sometimes it is difficult to write down frustration-free Hamiltonians, but there's a general recipe to generate frustration-free Hamiltonian from a simple model. Okay, so that is called like a Witten conjugation. So since I choose the ground state energy level of each local Hamiltonian to be 0, this local Hamiltonian is positive semi-definite. So I can always write positive semi-definite operator in this way. And I have a ground state, which is annihilated by every term of the Hamiltonian. So it satisfies this relation. Once I have this Hamiltonian, I can generate other frustration-free Hamiltonians the following way. So I introduce global operator M and local operator C. And this Hamiltonian is still frustration-free because this is still positive semi-definite as far as this C is also positive semi-definite. And I have a common ground state among all of these local terms because this, M inverse and M is cancelled. Okay? But they are not necessarily unitary equivalent unless M is unitary. Okay? So this keeps frustration-free nature and locality of the model. And actually, by fitting, by choosing these operators, I found that my model can be generated by Heisenberg Hamiltonian. So this is good and bad. My model was actually kind of secretly related by the related to the well-known example. But the point is that this M operator is not unitary. So this model is not unitary equivalent to this model. And so this is kind of like a non-standard kind of symmetry, right? Which is the subject of this conference. Yeah. So so from now, I want to present 3 new conjectures about frustration-free systems. The first one is about dispersion relation. So by analyzing many examples, I found if Hamiltonian is frustration-free and translation invariant and gapless, then in general, there exists at least some kind of variational state such that it is a translation eigenstate. So by translation by A, I get this standard factor, and the dispersion is soft in the sense that the difference between the ground state energy is bounded above by not a linear but some kind of quadratic order in the momentum with respect to some momentum. Okay, so this is just an observation by analyzing many different examples, and so this means that gapless phases with linearly dispersed linear excitation cannot be represented by a frustration-free Hamiltonian. Okay, so this is a kind of limitation of frustration-free Hamiltonians. So this is a related conjecture. I can forget about translation symmetry. Then what I found is that if Hamiltonian is frustration-free and gapless, then the finite size gap of Hamiltonian is actually bounded above by L to the L squared. Okay, the finite size gap is the following. So like even if the system is gapless, if I compute the spectrum in a finite box, in general, I find a finite size gap, right, to the first excited state. And I'm talking about this scaling of this, finite size gap to the linear dimension of the system. And so this is the general bound I see by analyzing many models. And this means that low energy effective field theory of frustration-free systems cannot be Lorentz invariant. And I have more basic conjecture, which is assumed in many previous studies without mentioning that this is actually a conjecture, or without mentioning that this is actually like an unproven statement. So in general, I can arrange eigenvalues of Hamiltonian in this way, in the increasing order. In general, if I want to define a gap to the Hamiltonian using this kind of sequence of sequence of the system size of the finite size box, then I would define a gap Hamiltonian this way. There might be the ground states might have finite size splitting, but this ground state manifold will kind of degenerate in the limit of large system size. And if the ground state manifolds and excitations have a separated in energy in the large L limit, then I say this system is gapped. Otherwise, it is gapless. I think this is a standard definition of gap. But in frustration-free systems, I found that this finite size splitting of ground state levels is actually absent even before taking the thermodynamic limit. And this is kind of common feature in many examples. For these models, I usually have some kind of splitting, but it is absent. And it implies that actually, when I judge whether a given Hamiltonian is gapless or not in frustration-free systems, what I have to do is to look at the first level whose energy is non-zero and see if this goes to 0 or not. So this simple criterion will give me whether this system is gapless or not in frustration-free case. Okay. And maybe I don't have time to explain this. And now I have a kind of proof of some part of the statement. So suppose Hamiltonian is frustration-free, then we consider an equal time correlation function of this form. G is a projector onto ground state manifold. And I choose some ground state. Okay, and I compute this correlation function. Okay, if it shows a parallel decay for x and y separated in space by order of L, then I can show that the finite size gap of this system is bounded this way. So this is a part of the kind of conjecture I mentioned, right? And the proof is actually very simple. It is based on this previous work by Gosset and Fan. So it is a kind of generalization of this Hastings comma result to frustration-free systems. So for field theorists, I think the exponential decay of correlation function in gapped system is just something assumed as something taken for granted, but it is a non-trivial statement in condensed matter systems. So Hastings comma proves that in general, a system with a spectral gap epsilon shows the correlation function can be bounded this way. It implies that correlation length C is inversely proportional to the gap of the system. For frustration-free systems, they kind of modify the result to this way. And what is important here is the appearance of this square root. So the scaling is now modified to a square root of epsilon rather than just epsilon itself. So using this result, actually, the proof of this result is a single line. I can assume that in this x minus y is order of L. So this is L, okay? But I'm assuming a parallel correlation function. So this exponent cannot be a positive power of L. So this epsilon has to be not only 1 over L. Because of this square root, I need to have 1 over L squared. So that is the proof of this result. Okay. All right. Can I have 5 more minutes or 3 minutes? 2 minutes. Okay. So so then I want to discuss an application of this result to kind of Monte Carlo estimation, which is slightly kind of different topic. But I think Geo in this morning talked about Monte Carlo estimation. So it is a simulation method of, for example, a classical stat-mech problem. So I think we all did this exercise, Ising model, this energy functional, and using the master equation and the local update rule and detail balance condition, and this kind of like a spin configuration is updated following this master equation. And there's a known phenomenon called critical slowing down. As the system approaches to critical point, the time it takes to reach equilibrium get longer and longer, proportional to the system size L. And this power Z is called the dynamic critical exponent. And people believe that this Z is greater than 2 without a proof. And see, like this is a list of the many different systems, and they all greater than 2. And people, I think, obtained smaller power of Z by giving up the detail balance condition or locality of the update rule. So that's what people usually do. And yeah, so I just wanted to show you, like a Monte Carlo estimation for Ising model, and it takes longer time as it approaches to critical point, or so this just shows that as system size increases, it takes longer time, right? And what is the relation to frustration-free Hamiltonian? I just discussed. That is, Markov chain with local update rule and detail balance condition can actually be mapped to a quantum frustration-free Hamiltonian in this way. So this is a like a update rule appearing in the master equation, and this is the Boltzmann weight. Then like I can write down a frustration-free Hamiltonian in general, and yeah, for example, for Ising model, I have this quantum Hamiltonian, which is frustration-free, and they share the same spectrum. So I can use the result I just showed you for frustration-free Hamiltonian, and this result of frustration-free Hamiltonian immediately imply that Z has to be greater than 2, and for a class of Markov chain Monte Carlo satisfying these two results. So I think like this is actually surprising proof of this result in general, kind of via quantum discussion, although this problem itself was truly classical. All right, so let me summarize my talk. So I explained to you 3 conjectures, dispersion in quadratical software. This is actually related to continuous symmetry breaking in 1 dimension. In general, finite size gap can be bounded this way, and some part of this scaling was proven for parallel decaying correlation function system. And I just mentioned, absence of finite size splitting in frustration-free systems is kind of widely discussed assumption, but which is not proven in general. Thank you so much for your attention.